Okay, we're all set. So, if you are coming in late or if one of your friends isn't here, let him or her know that I have the midterms back. I know you guys are going to ask what was the average and all that stuff. You don't remember. I think it was about 60. But if you come to office hours or whatever, I can check. I wanted to thank Professor Cunha for covering for me last week. I've actually been out of town for almost 2 weeks now, and it's funny how out of sync you get when you're out of town. So I came to here at 9 o'clock this morning, and I was like, why is the door locked? Where is everybody, you know? And then I realized class actually starts at 9:30, so I was totally out of it. I'd completely forgotten where we'd left off, so I went back and looked, and it looks like we were talking about common mode feedback. So do a recap of that, and then we'll start continue on with discussing OTA compensation. Okay, any general questions before we start? I think most of you also know by now that the homework deadline has been extended. A few people emailed me and said that they were having some trouble. It's a very important homework assignment, so definitely take your time, make sure you understand it. And also get started on the project because time flies, right? Okay, so let's recap a little bit where we were with common mode feedback. And if you remember, the idea was in a fully differential amplifier, as we know by now, we need some way of stabilizing the common mode voltage. And we discussed several techniques, and they all had some drawbacks. For instance, the simplest technique we could think of is you take the two outputs, let's say VO1, VO2, they're high impedance nodes, and we basically measure the average voltage between VO1 and VO2 with two resistors of equal magnitude, and that is in fact the common mode signal. And so we compare that to the reference common mode, and we drive some kind of feedback loop where this is some control voltage. Let's call it CTRL, and we call this VC, the common mode voltage. Well, let's call this VCM, and then we can call this VC, so some control voltage, to force the amplifier to return. This, of course, this should be a negative feedback loop that forces the amplifier to have the right common mode output. And then, as you'll recall, what are the problems with this approach? Okay.
Output impedance.
That's right. So this introduces loading, which lowers the gain. And then we also discussed that you can't make these resistors too large because large resistors basically require large area, but more importantly, they slow the feedback loop down because they introduce large capacitance, large resistance, RC time constant, and we get a really slow feedback loop. And so we may have a situation where there's a big common mode input signal that forces the output to have the wrong common mode value. Let's say this rails up or down, and this feedback loop is not fast enough to recover, let's say within one clock period. So we want this thing to be able to recover fairly fast. Well, we also introduced a way of avoiding loading by simply using buffers, right? That's what electrical, that's what circuit design is all about. If the impedance level is not right, use a buffer. So simplest buffer would be just a follower, and then we'd have the common mode signal here. And now we don't have to use large resistors at all. We could use relatively small resistors, and there's no loading effect because the gates of these devices buffer the output node. What's the problem with this approach? Seems pretty good, right? Let's get somebody new.
There will be a voltage drop, so the upper swing can be sort of.
Very good, yeah. So this will hurt our swing. So output swing lowered. That's because in order for this follower to work, this device has to be on, which puts a severe limit on how much voltage swing we can have out here. So the overall voltage swing of our amplifier, something that we work so hard to get as large as possible, is now lowered by this common mode feedback circuit. It seems like a shame to take a beautiful amplifier and ruin it with a common mode feedback circuit that has limited voltage swing. Okay, we looked at a couple more variations of this. Go and look at the notes. Just wanted to talk very quickly about the solution that seems to be very promising of using capacitors. And the idea of using capacitors is, instead of using a resistive divider, right? So the voltage here is a voltage division of this voltage minus this voltage, so we get the average voltage, or plus the voltage division of this voltage. Instead of using resistors, we could use capacitors. It's maybe not immediately obvious to you how this circuit works, but the way to think about it is, if I have two capacitors, and this is V1, and this is V2. So the idea is that if I have a differential voltage across here, let's say V1 minus V2, then this series combination of capacitors just looks like one equivalent capacitance, and I charge this side and this side up to some voltage to support this differential voltage, right? So this is V1 minus V2. Because this internal node here is floating, though, what's the net charge on here? It's zero, right? Because I can have negative charge here and plus charge here, and they cancel each other out, right? So if I want to know how much this voltage moves, well, let's look at another situation now. Let's say I introduce a common mode voltage. So this would be minus V1. In this case, I'm going to add V1 and V1. So it's a common mode signal. And if I move this voltage up to V1 and this voltage up to V1, there's no way, the only way to avoid, because I can't put charge onto this node, now I actually need to put a positive or negative charge on this node, right? Here I didn't need to because these charges perfectly balanced each other. Now I somehow need to put a charge on this node to support a voltage across these capacitors. I can't do that. There's no place for that charge to come. So the only possible solution is for this voltage also to go to V1. So now I have 0 volts across both capacitors, right? So this capacitive divider works. It's totally insensitive to differential signals because I have this charge balance. So as long as these capacitors are perfectly matched, this node will not move in response to a differential signal. But if I add a common mode signal, it will actually move up and down with the common mode signal. Well, this is great because I know that if I'm building an OTA, I'm actually going to have an output capacitance anyway. So this is really can just be part of my load capacitance. It's not going to introduce an extra load. In fact, from an area perspective, it makes almost no difference, right? Because I can take some of the output load capacitance and absorb it into here. I need that compensation capacitance anyway. Well, the problem, of course, with this approach is, I assume there was no initial charge here, right? And in other words, the initial state here is completely unknown to me. It could be that, there's some leakage over here. There's some during some processing, building of the circuit, if I just build an isolated node like this, I have no idea where this voltage really is, right? There could in fact be a net charge on this terminal, in which case there is a starting value of the common mode voltage which is not, so I guess the point is that this circuit will measure if the common mode voltage changes from its initial value, but it cannot detect that initial value, right? So I need to somehow reset this capacitor and put it into some good state, right? So one way to do that would be when you first turn on your circuit, I could have some switches here, which let's say charge up these nodes to the correct values. Let's say the correct common mode and the correct, let's just say for now I'll ground it. So now this node is at 0 volts, and if it moves away from 0 volts, that movement is exactly equal to the common mode voltage. So I can now compare this node to 0 volts, and I'm done. Well, is this really a good idea? Let's call this phi 0, the initial, let's say you turn on your circuit and you do this. Seems like a good idea, right? What's a potential problem with this? Well, how often should I reset these capacitors? If I do it once a minute, once an hour, right? Every second. Any ideas? There's no right or wrong answer, right? It really depends on your application. It depends on how much leakage you have. But it is kind of awkward if you have to do this, right? If it's a continuous time system, it would be very awkward to stop the system, reset this capacitor, and then come back. Well, fortunately, a lot of times we're not designing continuous time systems. We're designing clocked systems, right? We're doing analog operations in a clock period. So, in fact, why not do this every clock period? Right? Every clock period, I'm just going to come in and perform this operation. So let's say on the falling edge of the clock, I reset these caps, and then on the rising edge, I do my amplification or other operation, and circuit works, right? Is that reasonable? Anybody? Seemed like a good idea? Well, let me give you guys a hint. What am I doing to the output of my OTA every clock cycle? Okay, Shishi, you want to use a mic?
So the output,
Yeah, I'm shorting the output every clock cycle. Is that a problem?
you reduce, so main output resistance to equal 0.
Yeah, but that's only during the clock period where I'm not doing anything, right? Once I turn off my clock, the amplifier can operate as normal. So first of all, if this were an op-amp, could I short its output? Simple yes or no. If it were an op-amp, if you have an op-amp, would you short its output? Okay, somebody else. Anyone else? Okay, Lee?
No,
Why not?
because it's a voltage. Because it's a voltage source.
Yeah, and in fact, if it's a good op-amp, it has a short circuit protection in it to prevent it from melting down. With an OTA, though, no problem, right? It's a high impedance output node. I put a short there. It's a current source. Nothing bad happens. Or does it? Okay. Michael?
No, but I think you need to recharge the capacitor every time, I mean, if you have a small increment at the output, say, for different samples, you always discharge it and you need to basically fully recharge it again, so you lose kind of power energy.
Okay, that's a good point. Actually, what I'm more worried about is state. I'm destroying the state of this capacitor every cycle. What if that state meant something, right? What if I actually were using this, let's say, as an integrator? So this is what we call a switch capacitor integrator, and we're going to study this circuit a little bit later on, but let's call this CI now instead of CF for integrating capacitor. The idea of this circuit is very simple. The idea is that clock cycle 1, I charge this capacitor up to some input voltage, right? Clock cycle 2, I transfer the charge from here onto this capacitor. We've already seen that. So this capacitor is kind of a running total charge. Every cycle, I take some charge, which is proportional to the input, and I transfer it to this capacitor. So it's doing a discrete integral, right? So it's approximating a true integrator. We know we could build a true integrator with a resistor. So this would be a continuous time version of this circuit. This is a clocked version of this circuit, or switch capacitor version of this circuit. So this thing right here looks like an R, an equivalent resistor. The idea is that the charge moving across these terminals, on average, is the charge I put on this cap and then the charge I take off on this cap. So we'll study switch capacitor circuits later, but the idea is that now the state, the output voltage here is important because it represents how much charge I have on this capacitor. Okay? And there is a way to solve this problem, and I don't think the solution will make complete sense until we talk more about switch capacitor circuits, but I can give you an intuitive idea of how it works. So again, instead of charging these nodes directly to the voltage I want, I'm going to charge them indirectly. So this is VCM, this is VCM. This is the desired control voltage. Could be ground, it could be anything. And then I'm going to use, so let's call these cap C. I'm going to use these little sampling capacitors. And I'm going to do this over 2 phases. So phase 1, let's say phase 2, I'm going to charge up these sampling capacitors to the correct value. And then in phase 1, I'm going to connect these charges back onto these capacitors, and you're going to get charge sharing. And what you'll find is that because I choose this capacitor to be much bigger than the sampling capacitors, in one cycle this will not achieve the desired result. You have to wait several cycles for the charge transfer to occur over time, so that in over, let's say, 10 cycles, this will go to the right common mode voltage, but in such a way that it preserves the actual state of this integrator. Okay? Now, here's another intuitive way of looking at it. Again, this will make a lot more sense to you when we study switch capacitor circuits. These just look like resistors, right? This capacitor here looked like a resistor. These also look like resistors. So I'm isolating, I'm producing a filter between the output and the common mode circuitry. Okay? And this lets me preserve the state of this circuit. Yes?
When you explain why we cannot directly connect the VCM to the output, you say we're going to disturb the state of the CF.
That's right. This capacitor holds charge on it, right? And that charge is proportional to the running sum.
But we only disturb the state, the charge on the right side of the CF. Did not disturb the charge in the inverting node. So if in the switch capacitor, the only concern is the charge in the inverting node. Is that correct?
It's a good point, but it does in fact change. I'm changing the voltage here, right? If I change the voltage, that changes this capacitance. This is a virtual ground, right? And so this, if I set this voltage to 0, I've lost my running sum, right? Yeah.
Thank you.
That's because over time, the inverting node can also charge up to the right voltage.
excuse me, question?
Yes.
Can I just kind of reorganize like this? Because of the capacitor phi 1 and phi 2 looks like an R.
That's right.
So what you are doing is like put a RC constant, and you're trying to make this RC constant a little bit larger so that it does not affect whatever charge on the inverter capacitance right there. Is that right?
That's precisely right. You can
Okay.
redraw the circuit like this. Where these are the effective resistances of these switch capacitors.
So now the question, I guess, why we don't use real resistor is because of area or something else, or noise, whatever. Is that
Again, loading,
okay.
noise, speed, yeah. Speed is not a concern here because we're purposely setting them large. Okay, and then so we've talked about how to detect the common mode signal. The next thing is, how do you actually change the common mode output? And there's several ways to do it. And we'll use a very simple example. Turns out that there are several knobs in a given circuit. In other words, several places where I could change the common mode signal. So for simplicity, let me take a simple diff pair. And let me put current source loads here. So now I have V output 1, V output 2. And I know that I can't rely on the common mode signal to be, 0, right? Well, in this case, let's say mid-rail. I want the common mode signal to be somewhere around mid-rail. In fact, if I just build this circuit, it's probably going, because of the mismatches, it's just going to rail. So this output will be at VDD, this output will be close to VSS, or vice versa, right? So what's a good place, if I were to detect the common mode signal, where would be a good place to basically control the common mode signal? Right? Common mode is the average voltage here, right? If I want to move the average voltage up and down, I could change these two current sources, or better yet, I could just change this current source, right? So this is a good place to control the output. So what I do is I use my cap divider. This is C, this is C. Now this voltage is the average common mode voltage. I'm going to charge it up to the right value, let's say V bias. So this will set the circuit up close to where it needs to be, right? And then I'll let the common mode feedback move this voltage away from V bias in order to achieve the right common mode output voltage. So here I'm also going to add switches to bias this up to the right common mode output voltage. So during cycle 1, I force it to be in the right state. These are equal voltages. This is close to where it needs to be. And then I release these switches, and the actual output will move because this current value is not right. And as it moves up, this voltage also moves up, which increases the current, which now will pull this down, or vice versa. So you can see now I have a closed loop, a feedback loop, which is closed, and it has negative feedback. Okay, so this is actually a very nice way of implementing a common mode feedback loop with this simple amplifier. What's the gain of this common mode feedback loop? Jesse, you want to take a stab at it?
It'll be a pretty high gain because it looks like a cascade amplifier in the common mode.
Very good. Yeah, it's going to be high gain because I have this stage, it's cascoded by these two transistors, and then here I have a really high output impedance because of this mirror, and a really high output impedance because, remember, for the common mode circuit, this is not ground. This is actually another cascoded mirror. So I have a high gain. You also notice there is a small attenuation due to CGS here, right? So this feedback signal forms a voltage divider with CGS. And so basically that tells you how large you need to make C, right? Because up until now it seemed like I could use 1 femtofarad or 1 attofarad and the circuit would work. Well, clearly it's not, because if I use a too small of a capacitor, I get a huge attenuation, which reduces my loop gain. So, you know, C should be on the order of CGS in your circuit. Let's say to increase loop gain. So our loop gain is approximately the GM of this transistor times Z out times, let's say, 1/2 if I make CGS and C about the same. Okay. All right, so I have a feedback loop. What do I need to worry about? Yeah, stability. So any comments on the stability of this loop? What's the dominant pole? What's the non-dominant pole? For 5% of your grade, what's the dominant pole in the circuit? Frank, haven't heard from you in a while. Let's get you to wake up. Use the mic.
If I take a guess, I take the output.
Yeah, good guess. It's the output node. Right. So this is the high impedance node. There's really just two places where it could be. It could be here, here, or let's say three places. Here, here, or here. Right? This is the high impedance node. That's dominant pole. Here's a non-dominant pole. It's non-dominant because this transistor lowers the impedance of this node, right, to 1 over GM. So the non-dominant pole is on the order of the omega T of the device, divided by a factor of 2 or 3, because I got 3 transistors hooked up here. So it's actually pretty stable, pretty good. A question that comes up is, how fast do I actually need to make this loop? In other words, does it really even matter, right? And I think we talked about this a little bit already. You don't want to make this loop too slow, right? Nice thing is that it's already compensated automatically for you, because I'm going to have a big capacitance at the output here, and so it's going to self-compensate. But you want to be careful. You don't want this loop to be too slow, because if it's so slow that it takes it, let's say even a millisecond to settle, and your circuit operates on a microsecond time scale, then for 1,000 cycles, the output comm mode is wrong, and maybe the whole circuit's not functioning correctly. So it really is application dependent, but you just don't want to make it too slow. Okay? Questions or comments? As far as your homeworks are concerned, and even the project, you don't have to bother with these switches, right? What's a good way to do this in simulation? Initial condition. What's even a, yeah, you could do it that way, but it's actually kind of tricky. Easier way to do it. Yeah, just put huge resistors in parallel with these caps, so the circuit even works at low frequency. So the DC gain the DC operating point will be correct. Yes.
So for the frequency response, it seems for differential mode and the common mode feedback, they have same dominant pole.
Yeah, that's true.
So
but we're going to speed up the differential mode with feedback, right? I'm going to put feedback around this.
Okay.
That's going to make the differential mode really fast, right?
Okay, I see.
Okay. All right, switching gears a little bit. Let me zoom in on this part of the slide. Okay, so up to now we've really focused on single-stage OTAs, so-called single-stage. Let's say cascodes, telescopic, folded cascode. And these are very nice building blocks. They have high output impedance, which is something that we like for switch capacitor circuits. They're very power efficient. For instance, in telescopic, we share the same current with all the branches, so we have minimal number of current branches. There are some problems, though. They have limited gain. That's because we're just getting gain from one single stage. And our output range is kind of tricky, right? We had to play all these games with the bias in order to get good output swing. But at the end of the day, we're limited by the fact that we're using lots of stacking of devices to get good gain, which naturally reduces from our output swing. Of course, we can use gain boosting to even get more gain out of these devices. We've seen that. You have to be careful about the stability and the pole zero doublet. But if you limit yourself to just single stages, you're basically missing out, because if you introduce more gain stages, you can very easily get more gain. Swing is less of an issue because then you don't have to cascade if you're using multiple gain stages. And if you're operating on a low voltage, this is really important, right? Because swing is very dear. So what we'd like to look at, again, because probably you've already studied this in 140, is a multi-stage OTA. So again, what are the advantages of a multi-stage OTA? Again, the fact that we could increase the output range without interaction with all the other parameters. We can almost independently design how much output range we have. Disadvantage, of course, is power. We've got to dissipate more power. These current branches are now separate. We can't share the current branches. The biggest hurdle with a multi-stage OTA, though, is compensation. We're introducing multiple poles, right? And we all know that if you have more than one pole in your feedback loop, you have trouble. So we're going to look at different techniques of compensation. Miller compensation, you guys are all familiar with. Talk briefly about some of these other techniques, like using a preamp or using nested Miller compensation. Okay. So actually, this is kind of a follow-up here. So just as we've said, higher gain, higher swing. We'll talk a little bit more about this, how we could potentially reduce the input capacitance if this is an issue. This we'll come back to. Unfortunately, we're going to pay the price with power dissipation. And noise, we'll see that it's really not too much of a hit at the end of the day. So the only thing that's different is the design is going to be more complicated. So we have to deal with stability. Potentially, we're going to have to reduce the bandwidth in order to make it stable. And these are the approaches that we talked about. Okay. Questions or comments? I urge you guys to consider multi-stage amplifiers for your project, right? Since you guys are designing an OTA with a low supply voltage, using more than one stage may give you a much better trade-off. Who knows? I haven't done the project yet, so it's an open-ended question. All right, so here's an example of a simple two-stage OTA. You can see that the first stage is a folded cascode, right? I have my input diff pair. I fold it into a cascode. These are my cascode transistors. This is my output impedance. This is my output node. Before I would take the output directly here, right? If I take the output directly here, I have reduced swing because of these cascode transistors. But I can just add another stage, right? So I add another common source stage. This is my second stage. And now my swing is much better. I just have these two transistors to deal with, right? So I can go up to VD-SAT of each transistor, give or take. And it's common source stage, so I'm getting roughly the intrinsic gain of the device. So if I was getting a gain of 1,000 and I can get another gain of 10, I've got a gain of 10,000, right? All right, seems good. Remember when we designed this amplifier, stability was almost non-concern, right? Because remember our unity gain frequency was just GM over C, where C was the total load capacitance. And our non-dominant poles were occurring at this node, which is again on the order of FT of the device. So and the FT of the device, we could, just by biasing it and sizing it appropriately, we could make that easily a factor 2-3 of the unity gain frequency, And then even in the worst case unity gain feedback, you'd have no stability issues at all, right? Non-dominant pole is way high. Now I introduce a second stage, right? And this second stage is going to have a pole which could very easily compete with our original pole and introduce problems, right? So now I need to very carefully consider the pole at this node and the pole at this node, right? And for the time being, forget about this cap here, right? So I have to drive some load capacitance, and I know I'm going to have some internal capacitance. Let's call this C1. Let's call this C2. And so I have now clearly, but let's forget about this, I have two independent poles in my system. Okay. Questions or comments? Okay, well let's actually analyze this system. Let's say this is GM1 V1 R1 C1, and then I have another common source stage as follows. GM2 V2, this is V2, this is R2, and then this is C2, which is equal to CF. And this is my output. DC gain, of course, if I just had a single stage, it would be GM1 R1. Now I have a second stage, GM2 R2. So this is my total DC gain, and you can see I have two poles. Okay. So what's one method of stabilizing this amplifier? What's the simplest technique, the simplest approach to make this amplifier stable? I've got two poles here. They're of comparable magnitude. Okay, simplest. Maybe you could argue that is the simplest, but so you had to teach your little brother how to stabilize an amplifier. Would you teach him pole splitting, or would you teach him something simpler? Let's say your brother's 10. Okay. Yes, Jesse.
You can just add a big capacitor to one of those nodes and slow it down.
That's right. I can just maybe put a huge capacitor here or here and basically narrowband the amplifier. So make one of the poles dominant. Let's say I put it here. So this is called narrowbanding. And the way it works is if we look at a plot of the loop gain, let's say, so this is a single stage, and then with a two stage I actually add a second pole. Let's say the second pole is here. And if this is the unity gain frequency, so this is pole 1, this is pole 2, this is omega u, you can see now by the time I've hit unity gain frequency, I have total phase shift of 180 degrees, 90 degrees, 90 degrees, and I'm unstable, right? The thing, if I put a step into it, it'll either oscillate or it'll just clamp. So what I'm going to do is I'm going to just move the lower pole to a lower frequency. Let's say all the way out here. Okay, not a very good job, but you can see I need to keep going to the left. But as I narrowband this, at some point I will cross unity gain before I even see my second pole. So by narrowbanding this device, I come up with a new unity gain frequency considerably lower than what I could have achieved here, but now I'm totally stable because let's say this is a factor of 3 or 4 less than this pole, And so the extra phase shift I get here is very minor. Right. So this is what you might also call a brute force approach. Brute force, okay, I'm going to end up with a slower amplifier, but it's going to be really stable. I have no problem. In fact, in the limit that I make C very big, what's the phase margin of my system? Anybody? Yeah, exactly 90 degrees. So in the limit, phase margin is equal to 90 degrees, and it's a very stable system. Meaning no, basically no overshoot, no ripples, no nothing. But of course the price you paid is, one, lots of area, because you had to make this huge capacitor, and two, a really, really slow amplifier, right? So probably, you know, there are good places to use this technique. I mean, if it's non-critical and you've already got the capacitance, why not? Maybe in your common mode feedback loop or something, you can use this technique because you don't really care. But for the signal path, we usually don't want to give up all that gain. And so Miller compensation, which you guys all know, is a very, very good technique, also called pole splitting. So let's just quickly review how this works. All right, so let me see, is it worthwhile to do this? Yeah, we'll do this real quick. So let's again analyze the circuit, and instead of using, we're going to do, everybody here has studied pole splitting, right? Anyone who hasn't, raise their hand, and I'll call you a liar. All right, so we all know and love this technique. And the idea is I'm going to introduce a capacitance instead of to ground between these two nodes, where I know I have voltage gain between these two nodes. And what are the two advantages of pole splitting that you guys remember? Okay. Easy question, right? 140 question. Two advantages of pole splitting. Vincent.
That you move the poles into that direction, so it means that you do not have to have such a huge drop in the bandwidth while
Okay, let's do one at a time. So what, advantage one.
that means that you can compensate it without too much of heat in the bandwidth. And
okay, I think you're giving both reasons again simultaneously. All right, let me identify problem number one is lots of area, right? How does pole splitting solve that problem?
so you have a so you don't need to have such a huge capacitance. You just have a smaller capacitance, and then you still have.
Yeah, because we know this by Miller feedback, this capacitance is going to look larger by the voltage gain across it, right? And so I save area equal to the voltage gain. Voltage gain is 10, I save 10x area. That's pretty nice, right? Well, not quite 10x area, square root of 10. How about, no, it is, what am I saying? Yeah, it is 10. So what's the second advantage? And you already said it. As opposed to narrowbanding, right? What was the problem with narrowbanding? Why is it slower?
It's because you need to move the pole really to the left in order to have a phase margin. Now that.
And why not over here? All right, let's quickly review. Okay, I'm not going to derive this for you guys. So if I calculate the transfer function here, I have the DC gain. I have a 0 due to this capacitor, and we'll talk about where this 0 comes from physically in a moment. And then on the denominator, I get a second order transfer function. And let me just give you the full thing so you can verify this at home. Okay, so this is the value of A, and then this is the value of B. And these equations are kind of messy and they don't really tell you anything, but we're going to make the dominant pole approximation. In other words, we're going to assume that the system, after we compensate it, has a pole omega p1 which is much smaller than omega p2, because that lets me write this as 1 plus s 1 over omega p1 plus 1 over omega p2. I can just ignore this term because it's much smaller than this term, plus s squared over omega p1 omega p2. If I do that, then I can just equate the coefficient A with this dominant pole. So let me do that. So that gives me my first pole, and I'm going to just simplify it as R1cc 1 plus GM2 R2, which is approximately GM2 R2 R1 cc. Okay, and then the second pole, if I equate the coefficient B to this, I can solve for the second pole, and the second pole is approximately GM2 over C1 plus C2. Well, the nice thing about pole splitting is that what it does for us is not only does it let me use a smaller capacitor, but it also produces a second pole which moves up in frequency. And that's why we call it pole splitting, because both the poles move. And I'm going to show you, instead of looking at 3 equations, let's just look, first of all, see if these equations make sense. Okay? This one makes sense, right? Because it's just a Miller cap, right? I take this cap, I Miller multiply it, and that's the effect of pole 1, right? So this is Miller cap. Does this make sense? Does this, a lot of times when you do calculations at first, you get an answer and you wonder, is this the right answer? And you might have to sit down and think for 20 minutes or 30 minutes to convince yourself this is the right answer. You could just keep checking it and checking it and checking it, right? But you're not going to gain any insight. But if you sit down and really think about it, and then finally understand where this answer comes from, you could say, ah, now I see where this is coming from. It's definitely the right answer, let's say. So does this look like the right answer to anybody, physically?
Yes, I think we saw the CC. So when we're looking down, we see the resistance 1 over GM2.
Yeah,
and
very
then,
good, very good. So if I look at my second stage, I have this capacitance here. And this is C2, this is C1, right? And the idea is that at the frequency of the second pole, this thing almost looks like a short, right? Because this is a big capacitor. So at omega P1, it looks like a capacitor. At omega P2, it looks like a short, almost. So that means that if this are a short, the impedance looking here is just 1 over GM, right? And so the output impedance is dropped. Instead of being some large value, it's now just 1 over GM2. So if I look out here, I see roughly 1 over GM2, and so I would not be surprised if my second pole were a function of just GM2 and this capacitor, right? So at least intuitively, that makes sense to us. All right, so let me use some of these slides and avoid writing so much. Can we zoom in to here? All right, so what we've done here is we've taken the expression for the first and second pole and written them in a very, very intuitive way. So remember, I had GM2R2 here. That's the Miller multiplication factor. Well, what if I put in another GM here, GM1? Then I would have GM1R1, GM2R2. That's just the DC gain, right? So I can write the first pole as, then I have to introduce GM1 on the numerator, as minus GM1 over the DC gain divided by CC. Why is that very, very satisfying to write down? Based on what we've studied already. Should be jumping up and down, right? When you derive this result. Yes. Why is that?
Like the gain bandwidth holds?
Yeah, so what's the unity gain frequency? So if the pole 1 magnitude is GM1 over AV0CC, right, the unity gain frequency then is approximately AV0 times pole 1, which is just GM1 over CC. Right? And that's exactly, you mind zooming out? That's exactly the way we thought in a single stage amp design. We knew the unity gain frequency was the GM of the input transconductors divided by CL, right? So now we see that CC is playing the role of CL in our circuit. Otherwise, the design is almost the same. Once we pick CC, we pick GM1 to get the desired unity gain frequency. And then also the second pole we found to be GM2 over C2. Already we understand what's going on. And just to give you some intuition for why pole splitting is good, if I just use narrowbanding, the only effect I had was to lower one of the poles, right? If I use pole splitting, think of pole splitting as feedback. I know feedback lowers the impedance, right? It's shunt feedback around my second stage. So this is shunt feedback. And what it does is that at DC, there is no feedback, right? Because it's a cap. But at high frequencies, this is basically the loop gain, the output impedance is going to lower by the loop gain. And so in the limit, I just see 1 over GM of this device. And so it's kind of an interesting thing to do. You're designing a feedback amplifier and you want to stabilize it, so you introduce a second feedback loop inside the amplifier, make sure that one is stable, and then that somehow helps your overall feedback, right? So I've introduced 2 feedback loops. But it works. It works very well. What's a drawback to this approach? In fact, I'll put up this slide here as a hint. Again, let's zoom in over here. If you're a fast reader, you can just read here and give me the answer. What's the drawback of this approach? We talked about how great it is. It makes my second pole really broadband because it introduces feedback. So not only do I get a nice low frequency pole, I also get a really nice high frequency second pole. Okay? Life is good, except I use the mic.
Use 0.
Well, what's wrong with the 0?
If it's a right-hand plane 0, then it degrade in the phase margin.
Exactly right. So this 0 is in fact the right half plane 0. And it adds 90 degrees of phase lag, right? So remember, it's not a left half plane 0. For a left half plane 0 would help us, right? It's a right half plane 0. It's going to make our amplifier even less stable. So now instead of getting just 90 degrees from another pole, we also get another 90 degrees from the 0. And so the overall transfer function potentially could now be unstable again. Okay? I guess it's good to realize where the 0 is coming from. So this is my amplifier, and the idea is I'm going to connect the voltage here, and I'm interested in the output current, right? Apparently there's a 0 in this circuit. What's happening is I really have two paths to the output. I have GM V1, right? And I also have a current V1 times SCC. At some frequency, these two could equal each other, right? And if they do, at low frequencies, this is negligible, and this dominates. But as frequencies get higher and higher, this term gets bigger and bigger, and at some frequency they can be the same, and I out can go to 0, right? And at the frequency equal to GM over CC, this in fact is our 0. Is this going to ever physically happen? Is there a frequency I can go in on my oscilloscope and dial it in and observe 0 output? Comments or guesses? Nobody? Somebody's got to be awake, right? Is this frequency physical? Let's say this frequency is at 100 megahertz. If I go in the lab and put a signal source at 100 megahertz, will I observe 0 output current on this device? Yes or no? You can let someone else answer the why not. Alright, obviously the answer is no. You're thinking of the why not. Alright? Nobody? Okay, you guys are just tired or sleeping or whatever. Still on spring break, let's say. Well, remember, this is not on the j omega axis, right? So this is some 0 out here. Unless this 0 occurs on the j omega axis, right, it's not a physical 0. So I will never actually see, if I plot the Bode plot, which is a plot along this axis, I'll never actually see the current go to 0. Nevertheless, even though this does not occur on the j omega axis, I still feel its phase, right? So this is the phase of the various poles. This is the phase for a really far out pole. It almost adds 0. This is a phase for a really low frequency pole, right? It almost adds 90 degrees. This is the phase for a far out 0. Again, it adds almost 0. But if I get to a high enough frequency, I will feel the full 90 degrees of this 0 as well. And it looks like a lag in my transfer function. So that's where the 0 comes from. And we have to watch out for it. Okay, questions? Let's see why we have to watch out for this 0. Okay, so here's kind of a closed loop design. Let's zoom in over here. Okay, so if I'm going to design an amplifier, I'm going to put some feedback around it so I know the unity gain frequency is going to drop by my feedback factor, right? We just found unity gain frequency for unity feedback is just GM1 over CC, and so this is the factor F by which it drops. And then we know that we want to select our second pole to be sufficiently larger than the unity gain frequency such that we get the desired phase margin, right? What's a good value for K? Yeah, we talked about this a lot. Maybe between 2 and 3. If you can afford it, 10, right? Just get rid of it. But if you can't afford to completely get rid of it, make it 2 or 3. You have nice, good phase margin, and might even help your settling time just a little bit. So basically, I can take the expression for the second pole and equate it to K times omega U and solve. If you do that, you find what value you need to make CC. So CC needs to be a value of KFC2 ratio of GM1 to GM2. C2, if you'll remember, is your load capacitance, right? So this tells me that if I make load capacitance larger, I'm going to lower my phase margin unless I make CC even larger. So unfortunately, CC is not independent of CL. I can't just arbitrarily choose CC without regards to how much capacitance I have to drive. I have to make CC large enough so that I have sufficient phase margin. And this is the exact equation which tells you how to size CC. If you look at this ratio here of GM1 over GM2, there's no magic to it. It's not going to be 1,000, right? Because GM is proportional to square root of I. You know, device sizes are roughly going to be the same. Currents are going to be on the order of magnitude. So maybe this factor here is, you know, on the order of 1. So really, there's a direct relationship between CC and C2. They have to be on the same order of magnitude. Now, the issue with the 0, if I look at the 0 with respect to omega U, or if you like, if I look at the 0 location, how much larger is the 0 than the second pole? And the approximate expression is that it's larger by CL over CC. So clearly, this 0 is not too far away from this pole, right? Because I just told you I want to make CL and CC roughly the same to satisfy this equation, which implies the 0 is also your neighbor. You have to worry about the 0. Okay? Question? All right, so how do I solve this problem? How do I deal with this bad neighbor? You could move, right? You could ask your neighbor to move. You could kill your neighbor. Okay, I'm not advocating violence in this class. Any ideas? Well, how about you build a really tall fence so you don't see your neighbor? Anyone think of building a tall fence? I mean, clearly, you're going to have to deal with this neighbor, right? Can someone think of an analogy of building a tall fence? Maybe another analogy is you build a mirror. You build this big mirror, and so every time you look in the direction of your neighbor, you see yourself. You don't see your bad neighbor. Any guesses where this analogy is going? Bad analogy. Well, what we could do is you could unilateralize the feedback. Unilateralize the feedback. So this feedback capacitor, if I build a circuit like this, remember this 0 occurs because there is this feed-forward current. If I put a buffer here that's unilateral, then I still have my feedback, which is useful, but I don't have my feed-forward. And that gets rid of my neighbor, right? So this is that big wall, and I coat it with silver so I only see myself. So if I look from this direction, I don't see the bad neighbor. Okay, it's a bad analogy. How do I actually build this? Well, I could build a nice buffer. probably is going to be something simple like this. Just a follower. Comments? Do you guys like this approach? Actually, I think just to give you a little history of this, if I've got my history right, Yanis Savitas was a graduate student here at Berkeley, and he designed the world's first MOSFET op-amp. And then he ran into this problem. It was not stable. And I think this is the approach he took. Any comments?
Can you put a diode there?
Can I put a diode there? Where?
Buffer.
How would that help? Okay, but AC current can flow. I see your point. You're saying, let's put a diode here. Certainly a diode would prevent DC current from flowing, right? But AC current can flow back and forth, right? For a small signal perspective, the diode is just a resistance of 1 over GM, right? Okay, why do you guys why aren't we done? Why is there 10 more minutes of lecture? Any ideas? What are the problems with this? It works. It works. It does actually get rid of that 0. Think back. What's one of the reasons we went to 2 stages? One was to get more gain, right? What was another good reason for going to 2 stages? Headroom, yeah. Does this help or hurt our headroom? It hurts it, right? Just like that beginning of the lecture, we use this for common mode feedback, right? Now again, we've got an issue. We've got to keep this device on, which limits the output swing, right? So not a good idea, right? If you want good headroom, this is going to hurt you. Also, it adds current, right? I've got to have a separate current branch here, so I'm actually going to pay the price with current. Okay, well, you had an interesting suggestion of using a diode. In fact, this is a way of solving the problem, believe it or not. Not a diode, just a resistor. If I take my capacitor and put a resistor in series with it, it's going to actually move my 0. This is like the analogy of asking your neighbor to move. This resistor helps your neighbor move. So if you could have your neighbor move anywhere, where would you have this bad neighbor move? Far away, right? As far away as possible. Let's say infinitely far away. So how does a circuit work? Well, let's say that my 0, in fact, does move to infinity. At infinite frequency, this guy is just a short circuit, right? So this is GM V1, and the current through here is just V1 over R. So my 0 now occurs at infinity, so V1 over R is equal to GM V1, which tells me that R should be equal to 1 over GM. So if I make this resistance equal to 1 over GM of this device, I move the 0 out to infinity, and now I don't need to worry about it. Sure, it adds phase lag at infinity, but I'm sorry, I don't care about infinity. I have infinite gain I have 0 gain at infinity, so it doesn't really matter. All right. How am I going to do this? I could use a physical resistor, right? I could use another transistor. I could actually use a transistor whose GM is matched to the GM of this transistor, so this matches over process and temperature. Look back in your notes, we talked about circuits that let you design GMs that are matched to resistors and vice versa. So this technique is pretty effective, very commonly used. If you build a MOS amplifier, almost always if you use the Miller compensation, you're going to use this technique. This is called a nulling resistor. quick question for you guys. Why is it that if you build a bipolar op amp, you wouldn't worry about this? So if R is equal to 0, the value of the 0 is at GM2 over CC. As I said, history lesson. Build the world's first MOSFET op-amp, all of a sudden you had to worry about this 0. Why was it that up to then, nobody had ever worried about this 0?
Because the GM of the BJT is just too higher than MOSFET.
That's right, yeah. If the GM is sufficiently large, this 0 occurs at very high frequency, we don't worry about it. When you went from bipolar to MOS, especially the first generation of MOS, GMs were so low that this 0 was very important. Okay. Okay, a couple other techniques of mitigating this 0. This is actually quite clever. Let's zoom in just to the schematic here. So instead of using a... Well, this idea is not as clever. I thought it was another idea, but this still is not too bad. So the idea is instead of using a buffer, I'm going to use a cascode. Let's see how this works. So remember, I still want feedback current, right? That's the feedback current is what's giving me all the benefits. Feedback current lowers the impedance and gives me a high frequency second pole. So if you look at this cascode transistor, the feedback current comes here. It sees a low impedance looking into M11, and the current basically flows back, right? And on the other hand, if you have current going in the other direction, it's basically going to see a very high impedance, and it's basically you're going to get no feed-forward current. So this acts a lot like a one-way block. It's like the effective of an AC diode that you're talking about. This node here is effectively grounded by the low impedance of M11. So this transistor is biased with enough current so that this voltage swing is quite low, in which case it looks like this capacitor really, well, actually what we want is this voltage should be equal to this voltage, right? And so if you have a voltage variation here, that gets divided by the voltage gain of the cascode and appears here. And so this node is effectively grounded. So I was right originally. So you have a feedback current which is just V out over 1 over SC, and that's the right feedback current. Now there are a lot of problems with this approach, and it works, but let's look at the problems. Okay, so what are some of the potential problems with this? Well, I'll give you guys a hint. First of all, we have more current, right? So just like the circuit that we talked about before, I need to introduce I2. In fact, what's the advantage? I mean, why do we give this person credit, Ahuja, for inventing this? This was not the first way of getting rid of the 0. Let's just zoom in on the circuit, please. So what's the advantage of this circuit over the previous approach? Why not just stick a buffer right here? Why use a cascode transistor? I take back what I just said. It is a great idea, actually.
So it doesn't lower the output swing? I mean, we don't have the VT drop?
Exactly, right? So if I hook up a gate to this node, I have a problem with the threshold voltage, right? It lowers the swing. Now I just have a capacitor hooked here. So this guy can rail to VDD minus overdrive to VSS plus overdrive, and so I maintain the swing without introducing a zero, right? So it's a great idea. It still does have some problems though. Requires more current, but so did the follower approach, right? So from that perspective, we're on par. It's actually a very subtle problem. You have to think about this for a while. Think about if you're designing an OTA, what do you care about? What are the specs you care about? You care about the gain, you care about unity gain frequency, right? You care about noise. What else do you care about? All right, this one's more subtle. Problem is slew rate. Remember before, when this capacitor is just directly connected to this node, the slew rate is determined by the current of the input transconductor, right? If I have a big voltage swing, this full current I1 flows through this capacitor, charges and discharges this capacitor, and that determines the slew rate. So the slew rate would be proportional to C and I1, right? I1 over C. What's the slew rate going to be determined by now with this device, with this configuration? Well, it's I2 now, right? I2 is setting the slew rate. And that means that if I want to have good slew rate, I have to make I2 as large as I1. So there's a big power penalty to pay here. Okay. There's another problem. I encourage you guys to look at this when you go home. There's actually a systematic mismatch. If these I2s don't match perfectly, very obvious, right? If these don't match, this node basically has to move in order to make them match, which translates into an input offset voltage. So mismatches in I2 translates into an input offset voltage. Okay. There's a last technique briefly talk about, and this is called another cascode compensation technique. In some ways it's even more clever because it says, you know, instead of introducing a new amplifier in the feedback loop, just use an existing cascode configuration. So let's go back to our schematic. So instead of introducing feedback loop around this transistor, can anyone see where I could introduce a feedback loop that automatically gives me the benefits that what we want? Well, you have a cascode transistor here, right? So what if I use this node as my feedback node? That works, right? It does what I want. It's going to be it's not going to be a single stage. It's going to be a multi-stage amplifier. But effectively, it has the property that I can introduce a feedback without introducing a zero. We'll talk about this more next lecture. And don't forget, if you didn't pick up your midterm, come and get it from me.